In previous videos, we've been looking at applications of Maxwell's equations, and now we're going to turn our attention to a specific solution to Maxwell's equations, which are known as electromagnetic waves. Electromagnetic waves are a very important topic because various forms of radiation, such as radio waves, light waves, infrared, ultraviolet, and so on, these are all examples of electromagnetic waves. Here is an outline of what we will be discussing in these series of lectures. We'll first derive the wave equation from Maxwell's equations, and then look at a very specific solution to the wave equation, which is known as a plane wave. Plane wave is a specific example of a more general class of wave solutions, which are known as transverse electromagnetic waves, and we will review properties of those towards the end. So we need to begin with Maxwell's equations, and before we talk about these points here, let's just pull them up. So these are Maxwell's equations in point form. And we have been spending a great deal of time in our course solving for the fields, mainly on the left-hand side of these equations in the course. For example, we have solved for the D and E fields when we looked at electrostatics from a charge distribution. We've also solved for the B field, or magnetic flux density, when we looked at magnetostatics. And we know that B and H and D and E are also related. So collectively, D, E, B, and H appear in Maxwell's equations and are the fields that we've been interested in trying to solve for in this course. So we should think about what are the sources of these fields? What caused the D, B, E, and H fields to come into existence and be non-zero? The sources are, of course, in electrostatics, they were charges or charge densities, and in magnetostatics, they were currents. And we can identify them in the point form of Maxwell's equations here. So charges are represented most generally in terms of a volumetric charge density, and currents in terms of a conduction current density, J. So any system where we have charges or currents is going to lead to the production of these D, B, E, and H fields, especially in a time-varying sense. Now, so we've identified rows of V and J as sources in Maxwell's equations. But another important point is that in a time-varying problem, charges tend to be in motion. And so we're actually less concerned with the rho sub V term and more concerned with the J term, because any charge in motion constitutes a current. Also, in a time-varying system, Maxwell's equations force E and H to be related, and we're going to see this is going to be the case when we look at what happens away from the sources. And we're actually familiar with this type of analysis. If we return to electrostatics for a moment, you'll recall that we had Poisson's equation, which said that the Laplacian of scalar potential was minus rho sub V over epsilon. And this is a non-homogeneous differential equation. The source is the rho sub V, and the field that we're solving for is V. But we simplified this problem by looking what happens away from the sources. So away from the sources, so if we're not looking at V within the charge distribution, but away from the charge distribution, then the right-hand side becomes zero, and Poisson's equation reduces to a homogeneous wave equation, a homogeneous differential equation, which is called Laplace's equation. So we're going to use the same idea here. We're not going to be concerned about what happens within the source, but what happens away from the sources. A very practical example of this is if we consider your cell phone, and let's say it's an older cell phone with an antenna that's external to the phone. There are currents flowing on that antenna, but we're not interested in really what is happening on the antenna itself, but what is happening away from the antenna in the source-free region. So the J is the source of the E and H fields, but we're more interested in what are the E and H fields away from the source. Now in our cell phone example, obviously there is still an antenna in a modern phone, but it's obviously internal to your phone now. So coming back to Maxwell's equations here, let's try to write them in source-free form. So we identified the sources in red, and in our previous cell phone example, we said that we were very, very far from the sources now, or not near, like within the source distribution. So these terms are going to become zero. So we also have some constitutive relations that relate D and E and B and H, and we've described this in the previous video when we were summarizing Maxwell's equations. So for example, we know that the electric field and the electric flux density field are related through a constitutive relation, which is shown here. So if I want to rewrite this first equation, I can say, that, which is Gauss's law, I can say that the divergence of epsilon times E is equal to 0. And I can divide both sides of the equation by epsilon, and I just basically get divergence of E is 0. So this is interesting. We've returned to the case where now the E field looks very much like the B field. It is not allowed to have a divergence anymore. So unlike static fields, in a time-varying system, E doesn't have a divergence, and we will see it only has a curl. The second equation, which is del dot B equals 0, that doesn't change because there were no sources in it. The third equation also doesn't change, but we see that the curl of E is defined by the negative time derivative of the B field, as it was before. Finally, the last equation, actually, let's return to the second equation here. We know that there is a constitutive relation between B and H. So another way of writing the second equation is that divergence of H equals 0. The third equation we can write in terms of the magnetic field. So we could write that the curl of E is equal to minus mu times the partial time derivative of H. And finally, the last equation, we've removed the source term, which is the J, and we can say that the curl of H is equal to time derivative of D, but again, we'll use our constitutive relation and pull out the epsilon here so that we can take the partial time derivative of the electric field instead. So what's nice about these equations that we've written here is now we only have two fields that we are concerned with, the electric field and the magnetic field. And returning to the previous point on the slide here, we said that Maxwell's equations force E and H to be related. And when we look at these new source-free equations that we have written here, we see that we've constrained divergence of E and divergence of H to be 0, which is just, they can't have a divergence, they can only have a curl. But their curls are interrelated. So this is the constraint between E and H that we see now. The curl or circulation of E is related to the time derivative of H, and the circulation of H is related to the time derivative of E. So now E and H are very, very tightly related with each other. So these two equations that I've highlighted at the bottom are coupled. We would like to solve these two equations at the bottom, but it's a little hard to do so because each equation is a differential equation of not only the E field but also the H field, and we would like to write a single equation in terms of E or in terms of H. So we can do that by making use of this vector identity, which is when it says that if we take the curl of a vector, let's say the E field vector, that is equal to the gradient of the divergence of E minus the Laplacian of E. So let's apply that to our curl E equation from the previous slide. So let's take the curl of E. So from the previous slide, we know what the curl of E is. It is the, if we go back here, curl of E is minus mu times dH by dt. So we can write this moving forward here as minus mu times the time derivative, partial time derivative of curl of H, because we've applied the curl operation. And it doesn't matter what order of operations we do, the time derivative or the spatial derivative or the curl, these can be done in either order. Now, we also know from the previous slide that the curl of H is related to the time derivative of E. This was equal to epsilon times the partial time derivative of the electric field. So let's substitute this in. And on the right-hand side, we're going to get minus mu times epsilon times the second derivative, or second partial derivative of E, with respect to time. The left-hand side, we're going to apply our vector identity shown above. So we're going to have gradient of divergence of E minus Laplacian of E. And that's going to be equal to the same right-hand side that we just wrote up above. Now, the first term can be dealt with because if we go back to our source-free equations, we saw that the divergence of E was 0. We're not allowed to have any diverging time-varying electric field anymore with these source-free equations. So this first term is 0 because we're in a source-free region. So we are left with a equation that has Laplacian of E. We'll get rid of the minus signs that we see appearing on both sides. And we see that the Laplacian of E is related to the second time derivative of E. So now we have the equation that we were looking for, a single equation in terms of a single field quantity E instead of two coupled differential equations that mix E and H together. So this is a homogeneous differential equation because if I rewrite this equation and move everything to the left-hand side, then we have Laplacian of E minus mu times epsilon times second partial derivative of E with respect to time is equal to 0. The right-hand side is 0. Again, we have no sources, so there's no reason for this differential equation not to be homogeneous. Now let's define a new quantity here, which we're going to talk a bit more about later, but we're going to define u sub p to be something called phase velocity, and why it is called that will make a bit more sense later. Actually, let's, before we get into phase velocity, let's just call this wave velocity, because phase doesn't make any sense yet because we haven't, we're not using any sort of sinusoidal E or H yet. So let's just keep it general. Let's call u wave velocity. And let's define u to be 1 over the square root of mu times epsilon. So realize that u only depends on the constitutive parameters of the medium that we were studying the fields in, i.e. the permeability of that medium and the permittivity of that medium. So if we rewrite Maxwell or these this Laplacian equation for E in terms of u, then it's going to become Laplacian of E minus 1 over u squared times the partial time derivative of E, second time derivative, being equal to 0. And this is called the homogeneous wave equation. Because the right-hand side is 0, homogeneous wave equation for the electric field. And we could actually repeat this exact same procedure, but for the magnetic field. We could take the curl as a curl of H, and then write the right-hand side, and then rewrite the right-hand side using the other curl relation, this time using curl E relation. And we could arrive at a very similar, well, basically identical equation for the magnetic field, H. Which is also homogeneous a wave equation, but this time for the magnetic field. So now we've transformed our two coupled curl E and curl H equations into two decoupled equations for E and H, these so-called wave equations. In solving the wave equations, we're going to make an important assumption here, and that is going to be that the fields in the wave equation have a time harmonic dependence. We've actually seen this sort of assumption being applied before. In EC 110 and EC 212, when you studied AC circuits, you would have assumed time harmonic solutions when you were solving these AC circuit problems, and you were using a concept known as a phasor to do so. So we're going to do the same thing here. Here, for example, is the electric field, which is a vector quantity that is also dependent on 3 spatial variables, which we've captured in this position vector R, and also time. So E depends on 4 variables. And what we're going to do is we're going to separate out the dependence of E such that the spatial dependence can be captured in one term and the time dependence in another term. This is a little bit easier to understand if we look at a specific component of E. So for example, let's write out the X component of E if we were in a Cartesian system. So the X component of E is now a scalar equation, and it is given by real part of E tilde x, which is just one component, which depends only on space, times e to the j omega t. So we've separated out the spatial dependence of Ex in this term and the time dependence into this complex exponential term. So let's look at the first term. This is actually what we call a phasor. It's a scalar quantity, but it is complex, a complex number that captures both the magnitude and the phase of Ex. So we were going to let this be equal to, let's say, Ex naught for the magnitude, and then the phase might be e to the j, let's call it phi sub x. Okay, so you can see that we have a magnitude and a phase if we use this polar representation of this phasor. Meanwhile, the right-hand side is given by this complex exponential term, or the second term on the right, I should say, is this complex exponential, which is basically a complex sinusoid. So we take the product of these two complex numbers, the phasor, which depends only on space, and then this complex exponential term, which only depends on time, and we take the real part of that. So let's consider what happens when we do that. We're going to have the real part of, let's say, E x naught times e to the j phi sub x times e to the j omega t. We know that we can combine these exponentials into a single exponential, which is going to be e to the j, let's say, omega t plus phi sub x. And then when we take the real part of that, using Euler's identity, we know that we can split the complex exponential, let's say e to the j x becomes cos x plus j sine x, right? So the real part of that was the cos x. So the real part of this becomes Ex naught, which is, we already knew Ex naught was a real number because it's the magnitude here, a real number, times cos omega t plus phi sub x. So this is how we represent, let's say, the x component of the electric field. And now you can see the spatial dependence is captured in phi x. We haven't defined what phi x is yet. And the time dependence is in omega t. And we end up with an expression that depends both on space and time. But it's a nice compact representation when we use this phasor form, because before we applied this real part, we have this super compact way of capturing the information about the sinusoidal dependence of E and its dependence on space with this compact two-term, basically, expression here. So remember that this is just for one component of the electric field, which I've illustrated here, which is the x component. This equation up above here, it's actually three equations, right? One for Ex, one for Ey, and one for Ez. And you would have a separate phasor describing the spatial variation of Ex, Ey, and Ez. Okay, so now we can return to our wave equation. We see that the wave equation involves time derivatives. If we go back one step here, we have to take the time derivative of E, actually the second order time derivative of E, or the second order time derivative of H. And so before we substitute these time harmonic fields in, it's worth looking at what happens when we take the derivative with respect to time of these expressions. So let's return to this example that we have for Ex, just one component. So if I try to find the time derivative of Ex, which is a scalar quantity, and I need to do a partial time derivative here because E depends on space and time, then we're taking the time derivative of the real part of this phasor, E tilde, and this e to the j omega t term. Okay, So we can change the order of operations here and move the time derivative inside the parentheses here. But if we take the time derivative of e tilde x, that doesn't depend on time at all, right? So as far as this function in parentheses is concerned, the e tilde x is just a constant. And really what we're doing is we're taking the time derivative of the e to the j omega t term. So this becomes real part of e tilde x times the time derivative of e to the j omega t, which is just j omega times e to the j omega t. So this j omega term could be absorbed into our phasor, right? Because this doesn't depend on time. Omega doesn't depend on time. Omega is just a constant. And so in terms of what happens to our phasor, we can see that anytime we take the time derivative of a field quantity, it's the same thing as taking our phasor, e tilde x, and multiplying it by j omega, right? You can see that happening with the circled term here. If we had taken the time derivative twice to do the second order time derivative, then essentially we'd be taking the derivative of this function again, and another j omega is going to come down. So it would have been the same thing as taking our e tilde x and multiplying by j omega twice. But that just turns into minus omega squared, because j times j is minus 1. So it's the same thing as multiplying our phasor by minus omega squared. So let's try to apply this to our wave equation. We have here, let's take the first wave equation for the electric field, our homogeneous wave equation here. And let's deal with the second term in the equation, which is the second derivative of E with respect to time, assuming a time harmonic electric field. If we return to Maxwell's equations, we can now write Maxwell's equations assuming time harmonic variation of the electric and magnetic fields. So we had these equations on the left in the big circle, which represent Maxwell's equations in the source-free region. And now we can take this time harmonic definition of the electric field and apply it and basically write out Maxwell's equations in phasor form. So let's do that on the right-hand side of this slide and go through each equation line by line. So beginning with our first equation over here, del dot E equals 0. And in terms of a phasor expression, this means that del dot E tilde, which is our phasor expression, which only depends on space, is going to be 0. Same thing goes for the second relation, del dot H equals 0. That's going to become del dot H tilde equals 0. Again, remember the tilde refers to the phasor part of the fields that we've been talking about. The curl E equation can also be changed down here. So we have curl of E tilde, which only depends on space now, is equal to minus mu, but then we have a time derivative of H, and we see that turns into a j omega. So we actually have minus j omega mu times H tilde. So this is nice because our time derivative just basically turns into multiplication by a scalar. Same thing for the curl H equation. If we adapt this equation, then curl of H tilde as a function of space becomes j omega epsilon times E tilde as a function of space. So these equations on the right here are Maxwell's equations in time harmonic form. And we can also adapt this to the wave equations that we derived earlier. So we have these homogeneous wave equation in E and also the homogeneous wave equation in H. So let's think about how this is adapted here. We have Laplacian of E tilde, our phasor E, minus 1 over u squared. And then we have a double time derivative of E. And we saw that that turns into a minus omega squared. So we put that here. And then E becomes E tilde, our phasor expression that only depends on space. So this is our new wave equation. It can be just simplified a little bit here. I'm going to drop just the dependence on r since that's a bit obvious now. We have two minus signs, so this becomes omega squared over u squared times e tilde equals 0. And the same thing is going to happen to our wave equation for h. So we'll write that down here. Okay, so in the second term has this omega squared over a mu squared term, and not mu, u squared. U is the wave velocity. And now we're going to define a new quantity, which is known as wave number. So wave number is defined with a symbol k, and is equal to omega times the square root of mu epsilon. So if we square this, this is equal to omega squared times mu epsilon. So if we take our previous wave equation, which was, let's say we write down the one for time harmonic e, we had plus omega squared over u squared times e tilde equals 0. Well, if we substitute, if we see here that k squared is actually equal to omega squared over u squared, because recall that u was 1 over square root of mu epsilon. So u squared is 1 over square root mu, or 1 over mu times epsilon. So 1 over u squared is mu times epsilon, and that's what we see appearing here. And then k squared becomes omega squared over u squared. So we can rewrite these equations in terms of this new wave number like this. And in fact, we can collect the operations on e tilde together. We're taking the Laplacian of e in the first term, and we're then taking e and multiplying by k squared in the second term. So an even more compact way to write this equation is to factor out the operations or operators on e tilde as shown here. And again, for completeness, let's just write out the corresponding equation for the magnetic field or magnetic field phasor. So these are the two wave equations that are being solved in time harmonic form. These are known as the Helmholtz wave equations.